she's already thinking in new research directions. And, well, I think that maybe she'll share a bit on the academician session. I think that we can wait maybe 1 minute until we start, because we have a lot of topics for today, and I would like to have some results for later, because this is going to be exciting.
Hello, everyone.
Hey, Shao.
Hi.
Hi.
Hi, Angela.
Hello. Well, I think that we can start. I'll share my screen here. I've written a HMD with a agenda that I'm going to try to flow through. And well, hey, Irving.
Hey.
That's a curious profile image. That's a robot. Oh, there is now a decentralized SDGs.
Hello.
Hello. So, yeah, what do you guys think it best? Maybe do a quick introduction how, because we have some new people here, the Vikram, Josonik, Decentralized, Irving, from Analytics.
Let's have a brief introduction round. That's cool.
Yeah, I'll start. Hi, everyone. So this is my name's Sean, but most people just call me YGG. And yeah, I hang out here in the TEC quite often. I like to participate in the working groups and join the community calls on Thursday. They're a ton of fun. And I host a lab space here on Fridays. They're at 8 a.m. PST, 5 p.m. CET. And they're just hack sessions to have fun, show off tooling, show off experiments, and collaborate on some projects. And yeah, I've been in this token engineering community now for several months, since October. I took the Value Flows Ecosystems course with Angela and Sebnum and the team there, and really enjoyed it. And yeah, this is a wonderful space to share ideas on token engineering, get connected with opportunities, and meet wonderful teachers like Danilo. And yeah, it's awesome to be here. I'm really happy these hacking sessions are happening. So, yep. And I'll pass it over to Omni Analytics. If you're there, Omni, but you're also muted. And if you're not there, well, we can come back to you. But I'll pass it over to Gia.
Hi everyone, I'm Jaja. I just joined BlockScience as a researcher. I am a cognitive scientist in training, and I am like widely interested in designing social systems and network science. I'm really excited to meet you all. I would pass on to decentralized SDGs.
Hi. My name is Mark, but I like to go by decentralized SDGs because I'm really passionate about the potential blockchain distributed ledger technology has for decentralizing the UN Sustainable Development Goals. I worked for the UN volunteer program. I was a UN volunteer myself, and currently working on a Reimagine UN think piece white paper on unicoins, which is sort of an internal token for the UN system. I'm also working on in an ITO working group on digital currency global initiative, so exploring the various manifestations of digital currency and looking at particularly competition, consumer protection, and dispute resolution. So I'm very interested in some of the emerging dispute resolution models. I'm a lawyer myself. And my passion is really around how this can, facilitate volunteering for the Sustainable Development Goals using best practice decentralization. So just looking to sit with the TC community and listen in and learn more. Thank you. Oh, and I will give over to exclamation 3 Vikram.
Maybe he's not there. What about Irving XEZ?
Hi everyone, my name is Irvin. I just usually put the XYZ at the end. I am currently, my team joined Kernel's batch 2, so I'm a Gitcoin kernel fellow for the next few months. And my formal academic background is in robotics and a bit of like the blockchain side. So I think for the past 2 years, I was looking a lot into behavioral economics and how that applies to sort of human-computer interaction and human-robot interaction. So I started doing some research in terms of applying smart contracts and the way that robots and humans interact, and so I wrote a few academic papers on that. And lately, I've been looking more into this area. I ran into you guys, the token engineering group, and I'm really interested in the behavioral economic side, and also how networks scale out, and other kind of interesting research factors that you guys are looking into. So I look forward to the next coming sessions and joining and learning a lot from you guys.
Awesome. Who should go next?
It can be you.
Okay. Angela, co-founder of the token engineering community, doing a lot of ecosystem work like the Token Engineering Academy, courses like ecosystem value flows, and hacking sessions with Danilo, and hosting this research group. And at the moment, also working on a general balancer AMA model in cadCAD. And then spinning up research or also network of people doing research on AMMs as a component building block in cryptoeconomic systems, as a financial building block, but also as a feature to achieve system goals in other networks for different purposes. So excited to bring AMMs and finance as a feature to Web3, or leverage it on a higher level. All right, Jan, have you introduced yourself? I think you're the one we are still missing.
Not yet. I am Jan. I'm originally from Slovenia. Otherwise, I live now in Netherlands. In my work, I work as a data scientist in fintech, but I'm super interested in crypto economics, token engineering, and just everything that has to do with incentives, kind of. Yeah.
That's cool. I think that I'm the last one, so I didn't present myself, but I'm a research engineer here at BlockScience, and I mean, I'm the one that is sort of grinding the gears on the research projects. And most of you, I think, that didn't go to a hack session before, but the idea of, let's say, of those 2 hours working sessions to actually, let's say, get the hands-on the code. So, I mean, we have our research plan, we have several steps that we have laid out, and this session is to, let's say, is to really make things happen. And given that, I think that I can share my screen here. So I think that, let's say, going through it maybe is the best presentation. So let me pick the screen here. Okay. So are you guys here seeing a HackMD document?
Yep.
Let me...
Yeah, we see it, but Danilo, we also see we could see OBS.
Yeah, I think there are... strange. It seems that it's only... Let me try another approach here. Yeah, that's strange. It's sharing two screens at once.
Yeah, I've had this issue with Discord as well.
Yeah, do you know any quick thing?
Yeah.
Let me see if I change to... Yeah, it's still the same thing. And that's the thing about the working session. Bugs happens a lot, so
Yep.
including when you are trying to share the screen.
So Danilo, though, the solution that I usually take, I don't know if this will work for you if you need two monitors, but I usually just unplug one of my monitors and it just immediately jumps back to the single monitor.
Yeah, and it's weird because I'll try to do that. So let me try here. Well, I think that I will need to do a hack here. So I'll simply drop that monitor and use one screen. I think that's the way. So let me arrange the windows here. Removing. Yeah, I think that's it. Just do some arranging here. Okay, I'm back. So I did to switch workspace here, but I think it's doing now. Okay, so here my screen. So as I say, I have a proposal here for agenda. I've put that document on the Gitcoin kernel. But what I was thinking about this session was to, let's say, if you guys, we had another hack session 2 weeks ago, where just to give a recap, let me go through the research plan here. On the last session, we did implement all the definitions that we've used on the research plan, in the sense that we have defined the optimality gap, we have defined how we calculate let's say, the quadratic match of a subgraph. Let's say if you go here to the definitions and you get the 0, the 1, the 2, the 3, the 4, everything is implemented. And that was done on the previous session. But what happens is that, let's say, there is a step here when calculating the optimality gap that is about, let's say, calculating the optimal subgraph. Because the definition of the subgraph is, let's say, you have the neighborhood subgraph, and you rearrange that such a way that the utility metric is maximized. And what happens is that our code for the optimizer had a bug. And let's say the topic of this working session today is to, let's say, is to actually build those optimizers again, but in a way that works. So just let me just checking if Discord is all right. Okay. So one of the ideas of those working sessions is that, let's say, if you guys, let's say, see anything and have questions about or want to comment anything, feel free to interrupt me because, let's say, most probably I'm going to be working on something here, but I mean, a lot of the things can be confusing or not. I'll try to, let's say, to share most of my mind as possible so that we can follow through. But anyway, for the agenda today, let's say, the first step was to, let's say, to introduce you to the need that we need to implement those optimizers. And in order to have those optimizers, there is some previous research that indicates some algorithms that we could use. So if you guys go to the bottom of that document on the reference, we have some scientific articles that we could use as reference. And actually, let's say, what happens is that those optimizers, that class of edge rewire optimizing, we don't have any Python function that is ready for us. So what is going to happen is that we are going to fork the network X repo and we are going to implement it on the networks library. Because, I mean, if you are implementing for this project, I'm almost sure that someone is going to need that again. So why not implement that function in network X instead of just keeping our repository? So we are actually, let's say, we are actually going to do some contributions to our open source data science library. So I think this is something. The idea is that we are going to implement two types of algorithms. One that optimizes through Monte Carlo's simulations, and another that uses simulated annealing. I can explain a bit the concepts when I go through the article. And the idea is that we submit a pull request for them. So let me remove that. Once we have implemented the optimizer and we are sure that it works okay, and I think I don't think we are going to handle bugs because it's a somewhat simple algorithm. Anyway, by having that algorithm, we can, let's say, calculate the optimality gap on the data that we have. We already have the notebooks all in place. It's really about, let's say, just changing the optimality gap call. And the idea is that, let's say, by the end of this session, we can see we are going to be able to see a histogram of the optimality gap over the Gitcoin grants. So my expectation, if the hypothesis is true, is that we are going to see a histogram just like that. But instead of having number of students, we are going to see number of grants. And instead of seeing grade distribution on the horizontal axis, you are going to see optimality gap, and it's going to be between 0 and 1. So let's say this one here would be the colluders cluster, and this one would be the organic cluster. Is everything okay so far? I mean, any questions, anything that you would like me to talk?
Danilo, can you just give a summary of the optimality gap again and what that means?
Sure. So,
And Danilo, quick question. Sorry, I'm in the token engineering GitHub IO, but can you post this HackMD link?
what the research plan 1 or the
one year?
Do you have the agenda open? I have put here at the links. So any reference that I would, I'll post that again.
Thank you so much.
So any link that I get, I'm going to put on that document here. And I mean, feel free to edit also. The editing is open, so if you guys want to take any notes on it or put anything, feel free. So just to do a very quick recap on the optimality gap, the idea is that, let's say, the idea of the optimality gap is to suppose that, let's say, when you get a cluster of grants or a grant, you can have, let's say, a certain utility function to it, which is quadratic matching on our case. And when for the way that we are defining here, we are interested in the optimality gap of the neighborhood subgraph of a grant. So optimality gap is a metric that is associated with each Gitcoin grant, and each grant has a neighborhood subgraph, which is a subgraph. So you have, let's say, that's the way that I would put it. Let's say you have the grant here that you are interested, and then let's say you get the nodes that are closest to it. So, and when you look at the Gitcoin Grants data set, what is going to happen is that first on expansion 1, you are going to get the contributors to that grant. On expansion 2, you are going to get, let's say, the other grant. Let's say you get the first order contributors, and you get all the grants that they have contributed to. And on expansion 3, you are going to get the contributors that has, let's say, contributed to those neighboring grants. And the neighborhood subgraph would be, let's say, would be the resulting set. This figure isn't 100% accurate, but I think it could provide a visualization for what I mean by neighborhood subgraph. So the idea is that every grant has a neighborhood subgraph. And one thing that we have defined here is that subgraph can have, let's say, a quadratic match. So if you take the quadratic match of all the grants on that subgraph, the sum of it is going to be the quadratic match of that subgraph. And what happens is that the quadratic match algorithm depends a bit on how you rearrange the contributions. So what happens is that you can optimize how you distribute your collaboration, so you optimize your quadratic match for that subgraph. So here we define the optimal subgraph is the neighborhood subgraph where the edge connective is rearranged so that the metric is maximized. That's why we need optimizers, because we need that for calculate the optimal subgraph through quadratic match. And the optimality gap is let's say, is the difference between the maximum quadratic match that you can get for a subgraph and the real one, let's say the actual value of that quadratic match. And it's between 0 and 1. If it's 1, it means that the subgraph is not optimized. It means that, let's say, it could be worse in terms of rearrangement. In terms, let's say, the collaboration structure is very inefficient. And if it's close to 0, it means that it's very efficient. It's very optimized. And our hypothesis is that, let's say, when you pick the optimality gap, our hypothesis is that colluders are going to have a low optimality gap because colluders are going to, let's say, optimize their strategy. They are going to make the most efficient use as possible of their structure.
That's making a lot of sense. So it's like a measure of decentralization or distribution, and then when we look at the optimality gap, it's kind of seems like a loss function that we would like to minimize.
Yeah, let's say if you are an attacker, and let's say, given that you are an attacker and given that you can have 3 grants and 10 contributions, if you do the best possible arrangement, your optimality gap is going to be 0. And our hypothesis is that the attackers, let's say, because all attackers are usually deliberate. Our hypothesis is that as they are giving deliberate total structure, they are going to optimize that, let's say, the arrangement. While organic grants are not going to optimize because you never know how people are going to contribute.
I would have if you don't mind, I'm going to try to give an explanation of the optimality approach to this whole problem space. Essentially, there's a graph, and it's in some ways an aggregate. It's somewhat organic. But if we look at a subgraph and we basically stop and we just say, suppose this subgraph was created by an attacker or a group of colluders, then how optimal was it from a value extraction perspective? Then, using optimality gap, what we're basically measuring is how far from optimal it is if we interpret it as though they were optimizing. Then, if they're really close to optimal, we might consider that it's possible that someone was optimizing. Whereas, it's not the same as saying that someone was necessarily solving that optimization problem. You're saying, when I look at this subgraph and I interpret it as a feasible point in the set of actions in an optimization problem, how does it compare to the optimal? And then if it's close to the optimal, you might suppose that someone got there by optimizing, but it actually doesn't mean that they got there by optimizing. So the logic is sort of circular. So it's really important to like understand that it starts with the supposition that someone's solving an optimization problem, that if they were solving that problem, how well did they do? And if we see that they did really well, we might take the implication that it's more likely that we got here by someone solving a version of that optimization problem.
Yeah, that makes sense. So it's like an entropy metric, which I see why we're going to the simulated annealing later.
Yeah, because let's say to calculate that optimality gap, we need to optimize the subgraph. So that's why we are talking here about Monte Carlo optimizer and simulated annealing, because that's the way that we get on that metric.
Very cool. That's quite clear to me at this point.
Yeah. So let's go to it. The first thing is to actually get on hands the algorithm for, let's say, doing the Monte Carlo and the simulated annealing optimization. So I'm really interested, let's say, getting the optimal subgraph. We have a utility function, and we want the reward so that we get the best possible subgraph. So I'm going to open the first reference here because I think it's the most clear-cut one. It's essentially a research article that went out on last year. And this is about having a hybrid approach to network robustness, where let's say you try to reward the edges while also adding new edges, so that you can, let's say, maximize certain metrics. And the idea is that, let's say, we are going to use some variations of their algorithm so that we can solve our problem. It's a very interesting article, and I mean, there is a chapter here about meta heuristics that, I mean, it's a good mind because it gives you an algorithm for simulated annealing, another one for great deluge, and another one for optimization through genetic algorithms. So, I mean, if you guys want a challenge after this session, given that Network X doesn't have those optimizers, implement integrate deluge, the genetic algorithm, I think that lots of people could use. And I mean, I really don't understand why Network X doesn't have those algorithms. So the meta heuristics are contained, I think, that on page 32. 32. So for example, I'll open here. I'll explain that in a bit. Because the simulated annealing algorithm is actually very similar to a Monte Carlo one. The main difference is that, let's say, the simulated annealing algorithm, you can accept, let's say, non-optimal choices if you are, let's say, given to a certain probability that depends on a temperature measure. I won't go into much details of why that algorithm. It's sort of related of let's say, how you deal with local optimal points. Because if you use a naive Monte Carlo simulation to optimize a subgraph, what can happen is that you stumble into a local minima and you don't get the global minima. And ways that you, let's say, you could mitigate that is like, for example, supposing that you can accept let's say, worse solutions if they, let's say, give you a better overview of the landscape. And there are also the other algorithms like the genetic one. So on this algorithm, we are going to do some things. So for example, as I said, the context of that article is that they add some edges. Let's say they can add or they can reward edges. But in our case, we are going to drop that term here because we don't need to add edges. We just need to reward them. So what is going to happen is that, let's say, we are going to select the edge at random, and we are going to simply shuffle the source and the destination nodes. And here is where the simulated annealing happens. And what is going to happen is that, let's say, if we don't want to do simulated annealing, we just want to do Monte Carlo, we drop that loop, that block here. But if we want simulated annealing, we keep that block. So in a sense, simulated annealing is sort of a superset of a simple Monte Carlo simulation. And this is going to be the reference that I'm going to use to implement our NetworkX optimizer. So the link for that article here, if you guys want, is the first reference here. Actually, on the RecMD document, I'm going to put a bullet point here. So let's say reference algorithm. So if you guys want to have a look on the PDF, it's there. And in order to implement, let's say, that optimizer into NetworkX, the first thing is to, let's say, to actually fork the network's repository. So let's do it. GitHub, NetworkX. I think that's it. Let's go to NetworkX. By the way, any questions? So I've forked NetworkX to my personal user. Now I'm going to clone on my one local folder so that we can work on that. It can take a while. I think that while we clone here at the left, we can think a bit on the folder structure so that we know where we will place the optimizer. But given how NetworkX is organized, probably I'm going to create a folder here at the algorithms folder, because let's say they sort of try to organize things around topics. So I think that I'm going to create a folder here called Edge Rewiring. Or maybe, I don't know, what do you guys think it's best? Edge Rewiring as a folder name, or maybe optimizers? What are your thoughts?
Optimizers.
Yeah, it could be. My concern with optimizer is that, let's say, on complex network systems, there are many ways to optimize a graph. I don't know if it is too general. I'm considering just create a folder called Edge Rewiring. I think it could be a bit more clear. But anyway, we have cloned, I've just cloned here the repository. So now we can open the code and try to think how we could implement that article. So let's get on here side by side. I'll open here the NetworkX folder. So let me open here, algorithms. So I'll create here Edge Rewiring. And I think that maybe a thing that could help is maybe have a quick look on another folder and see how they're structuring. So yeah, they're putting methods in files. Let us see how they need. Here they import everything that matters for them. And also some tests. The right thing when you do software engineering is to, let's say, to think a bit about tests, but probably we're going to need to take some shortcuts about that. So I've created here the Edge Rewiring folder. I'll create now a init file so that that can be a submodel. And I think that we should also add that to the init of the root folder. So let me search here. Yeah. So where we put from network X algorithms, want to Edge Rewiring, import everyone. So we don't have everyone, but at least let's say I can do those nice imports once I implement the algorithm. And I'll create here a file called simulated annealing optimize. Or even better, I think that we should simply call optimize. because maybe the method could be an argument. I don't know, just a thought. The idea is that, let's say we would have a function here called SLOptimize, but I would simply call optimize for now. It would take as input a graph. So, oops. So let me zoom in here and x.graph. And other things, actually we need to see here what are the arguments that they take. So they take to the maximum temperature. So let's put in there. Maybe I'll put SLOptimize. I think it's clear. And I think is that this also returns another graph. So okay. Let us see what more things we could have here. There is this probably, I'm sort of looking here at the algorithm on my right side and see what things are parameters for that function. So for example, there is this padd, but we are not going to use that block because, as I said, that we don't add any edges to our optimization problem. Okay, there is also another thing, a delta R at the temperature. All right. Oh, there is this also this other parameter here, maximum improve. I think this is sort of, let's say, maximum iterations while the optimization doesn't improve. So we could put that. I think that the default value could be maybe 10. So the initial temperature by default is going to be 300 and the maximum no improve is going to be 10 by default. Oh, and there is also the TDK. And I don't know what is a good number. Maybe actually this is sort of associated with let me think about that. By the way, do you guys have any thoughts about those parameters? Because I never did simulate annealing optimization before.
I think they seem reasonable to start.
Yeah.
I'm not sure either, but yeah, they seem reasonable.
Yeah, one thing about TDK is that it seems, I think it should be lower than 1, because if not, the temperature is going to increase instead of decreasing.
Mm-hmm.
Or maybe, actually, let's see. There is a repeat here, and that repeat repeats until the temperature is less than the maximum temperature.
Hmm.
So so that term here should decrease. Yeah, that's all right. So it's a weird notation, Tmax, because it's sort of
Seems like it should be min.
yeah, that's right. That's what I mean. That paper is a master thesis, so I'll put min. I'll be. By the way,
Do you
I'll
know
put
for
the reference.
sure whether how? Yeah, I was gonna say maybe you just need a min and a max because you are gonna run into potential issues with it running too long, and it might need a period that it stops no matter what. So you could be facing a need for both.
Maybe what we could do is also put a number of iterations. Let's
Yeah.
put that.
That's what for when I saw T max, I thought that they meant like the maximum number of iterations, and I mean min is in a sense the minimum number of iterations because it's a sort of stochastic convergence algorithm. If you don't go long enough, you get nothing, you get noise. But if you go too long, I mean, you could run forever without hitting an exit condition.
Yeah, let's go with the number of iterations, and well, we'll be learning while we try. So let's try to implement that algorithm here. So first we have a graph here. Let's say we have a graph that is in slice, and then we have a temporary graph. So let's call temp g, and it is equal to g.copy. And t is equal to temp_min.copy. Actually, this isn't needed. It's just to, let's say, just to make it super explicit what the algorithm is doing. And repeat. So let me, maybe the best way would be to do the following. We have for e and range and iter. If t less than t min, then break. So now we are on the main loop here. So instead of repeating until this is below the t max or t min or on definition, we are actually doing a loop here on the NE on a range, and we break if this condition is met. And what's going to happen is that variable here that is set the g star, it's always going to be updated. So actually, it's the thing that we are going to return. So let's put it. Okay.
Yeah, actually, from the looks of it, there's no exit condition. So it's just the thing is that they call Tmax is n iter, right? It says do this so many times, but the solution that it considers optimal doesn't necessarily come from the last time step. So G star is the best to date. And so as it iterates, it keeps track of the best solution and then keeps iterating. And once it hits what they call Tmax and what you call n iter, it stops. But it looks like it's just a fixed number of steps no matter what. Your solution was just the best one you found during that exploration.
Yeah. Yeah. Yeah, let's go through it. So we have
the point I'm trying to make is that I don't know that we need tmin because there's no exit criteria. You only would use tmin as a extra part if there's an exit criteria, because you would say if the exit criteria is met, then if you haven't gone at least tmin, keep going. But because there's no exit criteria, I don't think you need the tmin.
Yeah, that's right. I'll drop that term. I think it's unnecessary complexity.
I don't think tmin is an iterator because we're doing this decay operation. I mean, T is temperature, I believe, isn't it?
Yeah. Actually, I'll drop that conditional here because we need the temperature anyways. But anyway, I'll try to put the blocks here so that we can iterate on that. So first we have a block for, let's say, try to keyword edge.
Yeah.
And then try to perform. Yeah.
Quick thought though, Sean. I think that T is still sort of a proxy for time in an annealing algorithm because you lose energy over time, and once you run out of energy, the thing quote unquote converges. So it's not an iterator, but it's still sort of the T and the T decay characterize like progression because as you soak the energy out of the system, it loses the ability to evolve.
Nice. Yeah. That makes total sense. Like the marble landing at the bottom of the local minimum. Sorry, that's what I'm seeing in my head.
Yeah, there is another very interesting algorithm too, that is the great deluge here. But I think that this should be left for another session. Anyway, so let's go through it. I've added some comments here, so it encapsulates the first block here. So this one is about rewiring the edge. The second one is trying to perform the lock optimization. The third one is to keep track of it's improving or not. And the fourth one is about dropping the temperature. So let's go with the easiest one first. So T equals T TDK. So that's it. We have implemented that last line here. There is another thing is that there is a loop here. So there is a max no improve. So actually we are going to create another loop here that is for no improve in range max no improve. So what I'm doing here is to sort of, let's say, do that in a Pythonic way. So I'm just because this is sort of a boilerplate code. So I'll drop that. And the condition is the following. If this condition is met, then I can break. So if last R below R temp G, actually, let me think a bit. So what this code is doing is actually the following. While you having improvements in the given temperature, maybe it's not too trivial.
So I think we need a variable that's maintaining no improve. So we need like no improve, which equals 0. And when we get our R applied to our gtemp, we want to check if it's...
Yeah, it's because I was thinking if there was a one-liner for that, but maybe the best way for now is to do is just to, let's say, do it explicitly. So but this is being changed. So I mean, that's why I don't like while loops. Because one thing that I'm sort of reluctant of doing the while do is because I know that every time that you put a while, you run into the risk of having infinite loop. I mean, it's a thing that people that do algorithms love, but I don't like. And so let me try to understand exactly what is going on here. So we have this last R, which is not defined here. So we need just to... I mean, this is another problem that article. What's the initial value of last R? So I will suppose that is infinity. Or better, it's 0.
Yeah, 0.
Let's simply suppose that. And because this R is a utility function, so the larger it is, the better. So if the last R is below the new utility 1, then we set it to be equal to that. Else we something no improve. So what is happening is that, let's say you have a limit of how much you can try to update your graph before updating the temperature. That's it. That's what it means. So the last R is going to be actually here inside that loop. And let's go keep track of improvement. So here we encapsulate the fact that we are bounded by how much tries we can have before updating the temperature. But there is a side effect of that. I definitely don't like while loops. Let me try to think how not to use a while loop here. Yeah, I think there is no way escaping.
Yeah, I think we should just wire up the function.
Yeah, I think you're better off writing it with a while loop and then just flagging it for consideration later, because it's
Yeah.
a valid implementation. If we wanted to refactor it to use a better, more Pythonic approach, we can look into it out of sync.
Yeah.
And Danilo, I'm gonna need to split in a few minutes. Is there anything I can do for you before I have to hop off? This is pretty awesome, though. I'm a little jealous that I have to leave.
Yeah, it's okay, but the idea of that session is really to just grind and let's say grind and also make use of all the collective mean power. You guys are being super helpful. So okay, okay. So now we can simply do that. So if less there below new air, then less there equals new air, and no improve equals 0. Else no improve okay, I think that we have implemented that last block now. Even though I'm still a bit reluctant of putting a while block on my code. Okay, by the way, I'll do another thing here because this is just to make pretty, because we have a iteration ranger here. I think that we could put a iterator here so that we have a progress bar when we test that. And okay, now let's do, I think that the second thing that we could do is the step of doing the lock optimization. I don't know why, but I always like to work backwards because I think that working backwards gets you, let's say, a better overview at the beginning. And if you try to start, let's say, if you work from beginning to start, instead, I mean, you reduce your perspective of the code. But I mean, this is sort of a psychological thing. I just like to start from the end. So, okay, now we are going to try to perform the local optimization. So I think this is pretty simple. So let's say, oh, and we need to have the air here as a, so let's put air calable. So this is a function that takes a graph as an argument. And I think that we could even make that split. So if we import the typing library, there are several typing hints that we could use, like for example, calable here. So I could pass a type hint that, let's say, this is a function that takes a graph as an argument. So it makes more explicit. I just need to see why the warning. List. Okay.
Are you taking a graph or are you taking a digraph? Because I think they're separate classes in NetworkX.
I think that for now we can suppose a graph, and I mean I think that the graph it would be an extension, but and this would return actually this returns a list. I mean, it could be digraph, but I don't think it's very important now. And a tuple. The reason why I'm telling that it's returning a tuple is because I suppose that there are two artifacts from that. I mean, teaser, the quadratic. No, actually doesn't make a sense a tuple. Never mind. It should be a utility function. Actually, I was thinking another thing. Does it make clear why I used that syntax here on Calably as a type hint? So, for example, here at the first argument, I'm passing a list, and I'm telling that my R function takes a graph as an argument. And the second element here tells that, let's say, this function is going to return a float. So this is really just for documentation. And telling documentation, we could put that.
I'm gonna say it's more than just documentation. For anybody who's familiar with our, like a lot of our mechanism design work, we're almost always dealing with the domain range mapping representations of methods. It's a very like composability oriented way of thinking about operators. So thinking about those operators in terms of the objects they take in and the objects they spit out is part of what makes components swappable. So you can always, in theory, take something that operates on the same domain and returns in the same range and swap one out for another. So I actually think it's worth understanding what Danilo is doing here for a more broad application than just this specific instance of an optimizer.
Yeah. Oh, by the way, I just found a bug on their paper. Because look at that, you have a Tmax here being initialized as the temperature, but this loop will repeat until the time is less than Tmax. So what I mean is that, let's say this is just going to do one loop, one iteration. So this really should be Tmin. I mean, it's contradictory to definition.
Yeah, I saw that
Hi,
earlier,
Danilo.
and I was really confused by it.
Danilo, one quick question. So I have to drop off for some kernel fellowship meetings. I was wondering where I can find a list of scheduled meetings.
Schedule meetings. We have a Notion page. I have put on the agenda here.
Okay.
So we have this Notion page that, let's say, this is sort of our central hub for knowledge. I think that there is a calendar there, and if it's not, send a message on the Gitcoin that we are going to put afterwards.
Okay, awesome. And one last question: Do you have like maybe a YouTube playlist for a tutorial or workshops that you've done prior?
Yeah. So there is a YouTube. I mean, I don't know a playlist, but
Yeah,
I think that on Notion. Have a look if there is anything on the Notion. If it does not, send a message that we'll see that, because we do have videos. So
awesome.
I'll drop a link to the cadCAD Notion. There's a list of all the cadCAD templates and models of interest. So there's a lot more to dig into there. I'll drop that link in the TE Gitcoin Discord channel.
Awesome.
And
thank you so much, guys.
One more thing, check the general Start Here channel here in the TEC community, and you'll see, check the pinned messages there. You'll see lots of really good resources.
Will do. I'm on it. All right. Thank you so much, guys.
Awesome.
Thanks. Till next time. So let us see what the guys are doing here. So RG. What is RG? Okay. So the G we alt star is the graph after we have attempted to rewrite the edge. So let's put here. R attempt. And this would be R new. By the way, there is a notation trick. Usually it's better to, let's say, to put the object name first and the qualifier second. This is a good practice way that you learn when you do a lot of coding. It's a small thing, but it makes a bit easier to keep track of things. So I'll rename that. Okay. So on the block of rewarding edge, we are going to have a attempt, and on the localization, we are going to have a renew. So if R attempt is higher than the R last, no, let me see that. When is this guy updated? Yeah, I think it's R last. So if the attempt is better than the last, then temp G equals the attempt G. Or better, G attempt. So we have a G attempt here. If this is not true, then we have a random number, which is Z, that is equal to np.random.range. So this is a uniform number. I'll make it explicit here. And if E is above is less than a value, then temp G, it's going to be a temp G. Else continue. Oops, else pass. And the value is going to be delta, let's put it here, npx delta R divided by T. And delta R equals, I mean, how is delta R defined here? Is delta R the attempt less the last R, or the inverse, or the absolute? What do you guys think? Let me see if the article tells something. Well, I think that I will simply suppose then. R attempt last, R last. Is it clear why I'm doing that, or let me part NumPy here?
Now, can you expand on that, Daniel?
About the delta R thing?
Yeah.
So the people here at the article, they simply put a delta R term, but I don't know what this means in terms of hard definition. Because there are three definitions that I could think about. Because here we are having an attempt, where let's say on the first block here, we try to reward the edge. We get the graph, we reward, and then we have a new graph. That new graph can be better or can be worse. If it's better, we simply update it. If it's worse, then there is a probability that we accept it nevertheless. And the idea of that delta area, I mean, I don't know exactly. I suppose that, let's say, if you take the utility score of the attempt and subtract by the... But I mean, it's really mysterious because there is also this negative sign here. But I mean, when I follow through that, my sensation is that delta R should be attempt less the previous one, because the delta usually follows the direction of the change. And the direction of the change is the attempt. Let's say what has changed from the previous graph was the attempt. But it's a bit weird because and actually I'm not so sure about if that's the correct definition of delta R. So let me think a bit about what would we have. Delta R is if it's following the attempt direction and it's half filled, it means that delta R is going to be negative. And if it's going to be, that term is going to be negative, and there is another negative term here, this is going to be positive. So the higher the change, things are going to explode. Because let's say that term will follow a positive exponential. Something like that. And in order to be accepted, that handle number must be below that. Yeah, I think it makes sense to have that delta R. Because let's say this is making very costly if you change your utility just a bit upwards, you are going to make it very expensive. So it kind of makes sense. But there is this temperature term here. Let me think how this reflects back. So if the temperature is very high, it is going to be very... Yeah, high temperatures is going to be very forgiving, and low temperatures are going to be... So yeah, I think this is the correct definition.
So this is like early on in the simulation, we are willing to explore. There's sort of a higher exploration incentive. Because as t is higher, then this value will approach 1. And for y to be less than 1 is a very likely chance. So it's sort of as the energy decreases and we move towards the end of the simulation, there will be less sort of random exploration.
Yeah, it's going to be very costly to have that random exploration towards the end. So yeah, I think it's right. So at the beginning, you can have essentially you could pick any bad answer, but towards the end, you are very constrained. So yeah, it kind of makes sense. So I think that our code here for the local optimization is right now. We now need to... By the way, where did I put the R new here? Okay. So this one is actually to be R new. Just making delta R's. Yeah, I think that now it is consistent. The R new is that R G started here. And I'm going to define it here at the attempt. No, let me see. Actually, the G star is set here. So the R new should be set here. Not only that, but this also requires a R new here. So R new. Okay, I think this is right now. I think it's consistent. And this is going to return temp G, but also I'm going to return a tuple here. So last here should be initialized here. Is it clear why I'm doing that? I'm just making consistent so that let's say we keep track of the last and that is only updated when we want it. And actually this is going to return a tuple here. It's just to make things consistent. So the optimize function is going to return the graph and also the, let's say, the maximum value of the utility function that we got. Actually, I'm going to reverse the order here. This is a tuple. Okay, so the last thing that remains is to actually rewire the edge. And I think that there is maybe a ready thing here. So network X edge rewire. There may be maybe, I don't know if you have a function for that. No. Let's see. Swap. Still not. So I guess that we must select the edge at random. So I'll write here the steps. Select edge at random. Attribute random contributor. Attribute random grant. So that would be the steps that we should made, and then we would set those two ones here. So how do I select a random edge on network X? Let us see. Usually I like to see if anybody has a one-liner, because I mean it's always easy to add some complicated functions, but if you have a one-liner, it's easier to maintain. I think that I'm going to use that random choice. I've already used that before, and it's very terse. So I'm going to import the random library of the Python standard library. The edge is going to be, let's say, random edge. It's going to come from tempg.edges random.choice. So this is selecting a random edge. And then I need to change the source and the destination of that. Let me see what it returns here. So this is going to return us a tuple. So the first step here is done. Let us put here. Now we have those other two. We have to select a random contributor and a random grant. And now I'm thinking about it, I'm not sure if we can actually do a pull request of that to network X, because this is going to be too specific to, I don't know, maybe we can. Yeah, I think that we can. So let's add some new arguments. Let's see. How should we call Actually, before I think about the parameters, I'll simply do anything here, and then I will think a bit. But before that, I need to remember what is the attribute that we are using on Gitcoin for keeping track of of whatever a node is a contributor or a grant. So let me open the repo here, and let's take a peek at it. So I think we should have that on the definitions. So it's the type attribute. So the contributor nodes are going to be a node for temp g.nodes.
Node instead of n.
I think there is a better tactic. Instead of I calculate that inside the loop, I think that we could do that outside the loop, because probably this is going to be faster. So this is going to be a set. It's always important to have the types right. So the contributor node are the set of nodes. If the data.type, if the attribute type is equal to contributor. So this is going to be the set of the contributors. Actually, I'm going to call that a contributor set. And let's do the same thing, but for the grant. So the grant set, same thing here. Grant. Oops, what is wrong? Grant. And to attribute a random contributor would be to select that random edge and to simply, random contributor would be random choice contributor set. And random grant would be that. So here we select a random contributor and set. Now, how to attribute it? So let us see here. I think it's relabel nodes. Maybe there is a better way. So we would have tempg.remove edge, no edge, then tempg put edge. So here we have removed and added an edge, but still we need to append the data. So let me see how. Network X, add edge. I just need to see the argument for adding attributes too, so that I can pick the. Oh, okay, just to pass a dict comprehend, a started expression. Perhaps I will add before removing. So I think that's it. I think that now we have now the logic here for the rewire edge thing. And now we need to calculate the R attempt. So R attempt would be the area of G attempt. I think that's it. By the way, any questions about it?
Danilo, can you explain what we mean by attempt?
So back here to the article, what happens is that, let's say, we have two loops here. We have the loop for decrease the temperature, but we also have the loop where, let's say, we keep rewiring so that we can maximize the utility. The attempt is that, let's say, when I do a rewiring, I am doing a attempt. If that attempt, the utility of the attempt is higher than the previous one, I simply update. So the attempt becomes, let's say, the new one. The attempt here would be, let's say, the subgraph that I'm storing becomes the one from the attempt, if it's higher. If not, then we have that probability process. I mean, so what I mean is that, let's say, the attempt will become the output graph if it's better than the previous one, or if it's worse, but let's say it gains on the lottery of the temperature. The lottery in the sense that, I mean, we have that probability.
Yep, that makes sense. So it starts out by just removing a random edge and adding a random edge. Is that right?
Yeah, actually, I'm adding first and removing afterwards, but the order could be reversed. So what I do is I select a random edge, I get a random contributor and a random grant, and I simply exchange the, let's say, the contributor and the grant of that edge. So I'm maintaining the, let's say, the amount, maintaining any metadata associated with that. I'm just changing, let's say, the source and the destination.
Mm-hmm.
And well, if everything is all right with that, I think that we got our function here. But I think that I'm going to change strategy because I was thinking here that logic here of having the type here, it makes the code not so easy to make it recyclable. I mean, it's not easy to do recycling around it. And this could be a blocker for doing a pull request. So, I mean, I'll test this first on the Gitcoin repo, and I think that maybe we could think a bit more about that, of how we could push that to the actual NetworkX library. So this SS optimize, if you remember from the previous hacking session, let me remember. If you remember, we had a definition here for the grant optimality gap that we simply call the optimized graph connectivity, which is sort of what we were doing now. So what I'm going to do is just to do that. Let's say I'm going to put here the definition, or better, I had the idea here. Let's use that SLoptimize function the networks libraries, but I'm going to use a personal fork, so it's all right. And here, let's import the SLoptimize, all right. And what I'm going to do here is the following. I'm going to install the NetworkX from my computer. So every time that I call NetworkX here on my computer, I'm going to use that local instance. So let's do it. Pip install dot. Yeah, that's it. We have installed this new version of NetworkX. Let us see if it works. Let's do a quick test. Let me open here a notebook, the Optimality Gap. And I'm going to try to do an import here just to see if I can access that function that I've put on my fork of NetworkX. So from NetworkX, import SI optimize. Let me make sure that I'm using the right one. Okay, let's try again. No module found. Let us see why. Let me see here. I think that I got it wrong here on the init. So let me go back here. And I think that we showed. Yeah, it's strange. I always get confused on how Python handles those module imports. I never got to understand that. I think that I'm going to copy paste. Let me see how they do on others. There is this all here. So here they are importing the files. It seems to be all right here. Here we are importing the algorithms. Let me try to just import NetworkX. Yeah. I think that I'm going to do a quick hack. Let us see now. Yeah, I'll test that afterwards because this can quickly become a time sink. For now, I think that I'll just copy and paste that on our Gitcoin repo. I think maybe it's a more efficient use of the time. So I'll just copy and paste here. And I'm going to change that optimize graph connective so that instead of doing the previous things, let me see the return here, last, okay. We're just going to do that. SA optimize, subgraph.
Hey Danilo, you might want on the pip install dot, you can add the -e flag for editable.
You mean on the NetworkX here?
When you did pip install dot in the NetworkX directory.
Yeah.
When I do this, I always add -e. It's an editable flag, and it updates the install when there's changes made.
Yeah. That's interesting. So yeah, that's a nice trick. But anyway, I'm going to do directly here because I think I know that, let's say, manage dependencies can quickly become a time sink.
Yeah.
So, I mean, I know that trap.
Yep, me too.
So okay, I'm just doing some managing some dependencies here, Calably. All right. By the way, let me install the real network X again. And also do a commit here, so git checkout b CA. Just don't lose the work. Okay, this is just to make sure that we don't lose anything, because it's always frustrating when that happens. So I'll do the following. I'm going to uninstall Network X and install it again, but this time from the original one. So pip install Network X. Okay, done. So I've put here the SL optimize. I just need to do some changes here because this accepts a collab that only takes a graph. And I think that the other utility one, oh no, the utility one is right. And okay, it's going to return a graph and a float. It's very helpful to have those type hints because you don't have, you know exactly what to expect from them. So what happens is that this is going to be the best score and the best sub graph. And that's it. Given that, I think it's just a matter of we try to hunt our notebook again. We don't need to do any change to the notebook actually, because we have implemented all the workflow on the working session before. So let us see. I'll put that as markdown so that becomes a bit faster to debug. Okay. So first bug, this is an integer and we can't copy it, so fair. Now let's reset and try it again. The best part is when you get at the notebook part, because it's sort of the error festival, but let's say things get fixed fast. Let's see the second one. Too many values to unpack. Let us see why. Okay, I must pass data equals true here. That should work. Let's try it again. That seems promising. Let us see what we got here. Distribution. Where is my output? Yeah, that definitely seems promising. Let's see. Nonce. Why nonce? Weird. So let us see what's happening. Probably we're not getting that conditional here.
This is where we left off last week, Danila, remember?
Yeah, so this conditional is not being met, apparently. And I think that I will simply drop that. So let's comment that. Anti-optionality gap. So let us see what happens now. Division by 0. Maybe I can try another. Okay, I got you here. So actually, this is a conditional that says the optimal match must be above 0. So if it's 9, it means that the optimal match is negative or 0. So there is some problem going on here. Another thing that we could do is maybe test that as a optimize directly. Oh, but doesn't matter at all. I think that I'm going to maybe have a I think that I'm going to need to enter the detective mode. So let's dig into that. So here, actually, I'm going to import out the definitions here, so it makes it easier. The contribution graph is not defined. And from where this comes from? So how I define the, okay, it's G. And this is for a given grant, so let's get one grant. Let's pick, for example, this one, the Ethereum Hub. And let's see what we got from that. Let's first take a look at the subway graph. Okay, we have several nodes, so this is good sign. Now let's see the hill match. 0. If the hill match is 0, it can't go beyond because, I mean, no, it may be code. Let's see the optimal match. Also 0. That's weird. So my suspicion is that maybe we have a bug on the quadratic match function that we are using.
I was just mentioning that. Is there any case where we would have, any case thinkable, where we would have an optimized match of 0? No. I can't think of any.
No,
so real match 0 is possible, but not optimal match.
No, I don't think so, because in the worst case, the optimal match is equal to the hill match. I think that this may be some bug at the utility function. Because we have some contributions, we should have match. So I'm almost sure that there is a bug. So how I'm defining the utility function here? let me remember. Okay. So the utility function is the total quadratic match. I think that we need to investigate a bit that. So okay. Let's get the utility function of the entire graph. It's 0. And it doesn't make sense because there are a lot of contributions here. So there is something that is not wrong, not working on the total quadratic match funding. Let us see. So first thing, what is this threshold? Well, it shouldn't matter. And what is doing here? It's taking the sum. And okay, several things happening here. And when it could be 0? What is this match? I have this feeling that this match shouldn't be here. It should. Yeah, I have the sensation that this get node attributes match is weird. So quadratic match, grants, total match. Okay, this is the quadratic funding, not the quadratic match. So that's why I was thinking it was weird. So when I do matches, I get that. I get a dict. I get the values. Let me see how this guy is made of. So yeah, a lot of work, a lot of time that we spend sometimes building things is actually doing those kinds because, and most of the time the solution is super simple.
Makes it even more exciting.
Yeah, and you never know if you are going to solve or not. So, why I had the error? So I forgot to import here. This should solve. So let's see the print. So this is a dictionary. It is giving us several grants, and all the values is 0. So that print, I know that is coming through that. So here, everything that we are getting here, it's getting 0. So I'll take note here. I'll take a note so that I know that, let's say it's here that I mean, everything that happens after that, probably it's right, but there is something wrong before that. So here, for example, I'm just taking the graph, so probably this is right. So I have 2 blocks that I could investigate. There is this first block here, and there is the second one. And I think that the goal that we have now is to, let's say, is to identify where the bug is located between here, the beginning and the end. So I'll start by investigating here. So contribute, let's see what are the contributions that we have here. Let's make sure that, let's say, there is no bug here. And the best way to know that there is no bug a lot of times is just seeing what goes out of it. But I think it's all right until that block. Okay. So we can see here, for example, that we have tuples, we have contributors and grants and amounts. So no zeros. So probably the bug begins here. Okay, now we have 3 lines of code that we could investigate.
Danilo, all of those grants had the same amount. Was that a bug? If you jump back to that print?
That's a good observation. There is a bug here. Or it seems to be. So actually, let me see. I don't know if no, it isn't out the same because there are some that are 95. So it maybe it's just an artifact because we are just using a tiny subset of the data.
Okay.
So yeah, so we have those 3 lines here that we show the question ourselves. So let me see. I think that we should maybe a first step would be to make sure that the contradict here is what we expect. So let us see. Actually, I'm going to see everyone at once. I think it maybe be faster to see. So there is a nice Python trick that is to, let's say, to put a f string, but you put a equal signal here at the end. This is very neat. You'll see on my terminal how it works. So let's print that. Perhaps there is a better way of doing that, but I never took the time actually to research. But I am almost certain that there is a better way to debug that. So let us see now.
I've never seen this trick before, but I think I know what it's gonna do. And I think it's pretty cool. Yeah.
So you can see, for example, this is the contribudict, this is the pair totals, and where is the matches? Well, I'm not sure where is the matches. Okay, it's here. So the matches is giving 0, the pair totals is giving something 2, and this is giving something. So the bug is on the match project function. Well, we have the reduced our bug to just 1 line. Now let's investigate that function here. Let's see what happens. What could give a project total of 0? Not iterating. So if it's not iterating, let's try to understand what's happening here. Actually, I'm going to open two windows here because it may be best. So it's going to be a bit hard here, but just to give an overview, we were debugging the quadratic match function here. We have the contribudict and the pair totals. And we have 3 parameters that is being provided for the match project. Actually, let's go through it. We have a dict comprehension over all the projects. And I mean, there is this contribudict, which is a dict. The key are the grant name, and the value is the output of the aggregate contributions. So this project contributes is this first contribute. We are providing the grant here, and we are providing a dictionary with a dictionary of contributors. Is it clear? I mean, the hard thing of debug is that, let's say, when you are debugging, you always have to, let's say, the most information that you can have access the best, but at the same time, there is this information management issue where, let's say, it's really easy to get overloaded. And I mean, guys that do a good debugging usually are guys that, let's say, can handle well, let's say, that information overflow. We have the pair totals. So if I'm providing the contribs, essentially the argument that I'm providing inside the match project is this dictionary of contributors here. And the pair totals, we are providing a dictionary of dictionaries. Yeah. And I think there is a bug on that. Yeah, there is a bug on that. I think that the grants and the contributors are being mixed up, because if you get at those pair totals, the way that I understand that function, it's supposed to only have information about contributors. It's not meant to have, I mean, the keys should only be contributors. It shouldn't be grants. But we have grants inside here. I mean, yeah, there is a bug on how we process that data. And going to the match here, yeah, we would get all the contribs, do a lot of things. And why this is above? This is a strange term. Yeah, really strange. Just to comment what I'm seeing here. This contributes here on the match project is going to be that dictionary here. So we are picking the keys and the values, and we are doing a double iterator. And here I tell that, let's say, I'm only going to do something if one is above the another, but this is a string. This doesn't make a lot of sense. Actually, it makes a lot of sense to return 0 because, yeah, there is some problem with that implementation. Let's go to the source of truth. There is let's say, a vanilla quadratic fund implementation that we could use as a source of truth. Yeah.
Danilo, just a heads up, not to put the pressure on, but we've got 4 minutes till the top of the hour. I think we can solve this bug.
Okay, let's do it. So this is the source of truth. And yeah, they are doing the exact same thing here. Key I, V1 in 1. If it's above, then that. But it's really, really weird that that above key 2 must be above key 1.
Oh, Danilo, I think I know why they might do that. If it's edge traversal, are we seeing each edge twice? And so we just do a string comparison to pick
maybe.
So
yeah, maybe there is a. Yeah, maybe there is a implicit assumption that that dictionary should be ordered. So maybe there is this implicit assumption. But it shouldn't matter, actually. Yeah, it shouldn't matter. There is another trick that we could do. We drop that. Let's see. We just tell that it's different. And the project, and what we do is, let's say, is divide by 2.
We might
I
want
think
to.
this trick should work.
We might want to print P while we're here, just in case it's being 0.
Print P. Yeah. No, I don't know if it's worth it because the P depends on the pair totals. And we know the value of the pair totals.
Okay.
No one is 0. But maybe it's worth to print the project totals just to be sure. I think that the print total never got activated in the first place. Let us do another approach here. Let's print the contribs. Let's print here something. Print the matching the project. Let's do that and let us see where we get. Okay, now we have something here. So first thing is that there is some problem on preparing the data because these contributors should be only have contributors. It seems that all the projects being matched, there is only one contributor. And if we have just one contributor, we have this inequality here. So just to have a last try here before maybe one thing that we could do, because we are using a subset of the data. So we could change that from 15 to maybe 50. And let's see what happens. So this is the last try. Yeah, some problem. Yeah, I'm going to need to dig into that. Oh, what's this one? Let me see a thing. Yeah, because I saw some numbers and then yeah, I did.
Oh, the suspense is killing me. Okay, this is
Oh,
wonderful.
look at that here, matching product and.
Danila, I want to give
Oh
everyone
yeah,
a
there are
chance.
some numbers here.
Yep, we're so close here. Oh, it's killing me. This has been such a joy, Danilo. It was wonderful to see all the people in here, so many people. I want to give everyone a chance. I'm going to hop off. I'm going to move over to the TEC community call, which is happening now. And it looks like Danilo is wrapping up here. So I'm going to jump off. Danilo, I'll just let you, if people want to stick around, that's fine. The simulations channel is open. And yeah, I just want to thank everyone for coming out, and thank you, Danilo. This was a wonderful, joyous, and very exciting ride. So looking forward to next week.
Yeah, thank you so much. I don't know if the call is still open, Danilo. What was the last step? You seem to have something.
Oh, just to share my script, because we had a glimpse of hope here.
Exactly.
Yep.
I want to end
Yeah,
with a glimpse of hope, of course.
so yeah, what was happening is that, let's say, we have that we're printing here a matching project where we were printing the contribs here. And what happened is that before that iterator loop here was just skipping. It wasn't doing anything. And we know that because, let's say, we only have one contributor here, but then we got this one which have, let's say, several keys and values. So we started to print out those numbers, and those numbers are the project total. So it means that, the project got matched. So we had a glimpse of hope that maybe some of the projects wouldn't be nuns. But I need to do a debugging about that. So that was our glimpse of hope.
And we have a cliffhanger then.
Once again.
Yeah, just another
Next
cliffhanger.
week. Yeah.
Yep,
Or
tune in next
probably,
week.
guys, check it out. And can you share the repo again, so that probably if anyone wants to give it a try and come up with a solution.
Yeah, I'll do a commit to a branch, and I'll share on the Gitcoin and tell where we are. But probably I'm going to do some debugging this week, and we'll see for the next week.
Amazing.
Yeah. I think that we can. I think that we can finish. There is going to be a TA Commons call right now. It's going to be on the general channel. Sure.
Yep, that's right.
Yeah. If you guys want to join, it is going to be a super. It's a call that I think that everyone once in a life must attend. So, I really recommend to jump in and know the people, see how the Commons works, because it's a very exciting group and a community.
Awesome.
All right, see you there. Thank you so much.
Thank you, everyone.
Thanks, guys.